Puno is located at the southeast corner of Peru. Native communities who live around the Titicaca Lake have a long tradition of working with the totora reed that grows around the lake. They know the totora life cycle and how to work with it to make mats, boats, houses, and even islands. However, currently some communities are leaving this traditional practice, and large areas of totora have to be burned annually to allow for healthy renewal. Puno has many areas above 4,000 meters above sea level, where agriculture is not possible and alpaca breeding is the main economic activity. It is an isolated and harsh environment with few resources, cold and windy, but with intense solar radiation. People live here in extreme poverty. They live in isolated dwellings near the place where they have their alpacas. The climate is the same throughout the year, with nights below 0 degrees Celsius and days with temperatures in between 10 to 20 degrees, depending if it is a sunny or cloudy day. The typical house has 3 separate modules, and each room opened directly to a central patio. Walls are made of stone over earth floor, with metal tin roof and doors, no windows, and gaps among materials. In 2016, a strong earthquake hit Puno, specifically Orduña, at 4,800 meters above sea level in Lampa province. Houses collapsed, and people improvised shelters with the little resources available. Given the usual delay on government emergency response, they built their temporary houses with metal tin walls and unstable wood structure, thus thermally inappropriate. These circumstances motivated the team to start this project. The main requirements defined for the temporary house were 9. It has to be appropriate to the characteristics of the high altitude Andean region, for families of 4 to 6 members, and last for 1 to 3 years, which is an estimated time for the government to provide support to rebuild the permanent houses. Following the typical house organization, bedrooms, kitchens, and storage for tools and food are the main required rooms. It has to be lightweight, easy to transport through difficult roads, and easy to assemble by local people. Thermal comfort has to be provided with passive design strategies. The materials have to be locally available, thus the totora was considered as the insulation material. Costs have to be low, and the house can be disassembled to move it to another location or to reuse the materials for building the permanent house. The porous structure of the totora gives it its insulation and lightweight properties. The totora panel conductivity was tested at the university laboratory, and it confirmed that it is within the range of other insulation materials. We learned how the lake communities work the totora, how they saw their mats to cover their houses, and how they build and maintain their totora islands. Then we experienced with several combinations of totora sealants to protect them from rain and sun, and with wood frames to create totora panels, but they didn't work, and we went back to the typical totora mats. Both with closer seams and joining a mat with horizontal reeds with another with vertical reeds to make the panel thicker, with higher thermal resistance and more rigid, while still lightweight so that one person can handle it easily. The structure of the house is made of wood prefabricated elements, not only to support the house, but also to contain the totora panels. The temporary house has 3 rooms: bedroom, kitchen eating area, and entrance, which works as an airlock to reduce heat loss when door is up. It is half meter above ground level, and 2 skylights were added to increase direct solar gain. Doors and shutters of windows and skylights are insulated with simple totora mats. Totora panels were prefabricated by a family of the Chimu community, and the wood structure and other elements were made in Puno and Lima. The temporary house prototype was built in Juliaca in July 2019, was inhabited by 2 students and monitored from August to October. The exterior finish is made of wood boards and metal tin roof to protect the totora panels from rain and sun. 2 data loggers were located outside and 5 inside the house to monitor air temperature and humidity. These are the results. The solid gray line is the outdoor air temperature. It can be observed that the indoor air temperature swing of all rooms is less than outdoors, which demonstrates the insulation properties of the totora panels. This chart shows the result of the temperature of the exterior north wall, the light gray dotted line, which was exposed to the direct sunlight during the monitoring period. It can reach up to 28 degrees at daytime, while the indoor air temperature of the north bedroom and the kitchen does not go over 20 degrees. The goal was to maintain the indoor temperature at and above 10 degrees, which is the adaptive minimum comfort temperature for the region, but the temperature at night went below 10 degrees during the 3-month monitoring. If we compare the coldest days of the monitoring period with the temperature of a typical house of the high altitude community of Orduña, there is an improvement since the lowest indoor temperature of the temporary house is always above 0 degrees. Despite outdoors, the temperature is minus 10 degrees. We identified 3 main causes for these results. Gaps in some of the joints of the totora panels with the wood structure, the lack of thermal mass to store the intense solar radiation coming through windows and skylights, and the open connection in between bedroom and kitchen. So the recommendations to improve thermal performance were to install a door in between bedrooms and kitchen, to improve the adjustment of the totora panels with the structure, a better seal of the opening frames, and the installation of a closed system of solar panels to provide hot water to a tank located in the bedroom that can be insulated with totora mats during the day. At night, the totora mats are open so that the water tank releases heat to maintain a more comfortable air temperature in the bedroom. The prototype was dismantled in just 3 days and moved to the high altitude community of Orduña, where it was reassembled by a local family with some of the improvements identified. Currently, this family is living in it, but due to the pandemic, the monitoring equipment could not be installed. This research has demonstrated the insulation properties of the totora reed and specifically of the proposed totora double panel. It is still necessary to adjust some details of the assembly process to reduce the heat loss at night and to increase thermal mass indoors. It also provides an alternative for an appropriate and faster response when seismic or other events affect houses in the region. Thank you.